Please join me and the rest of the Optimum membership staff in welcome today's speaker, Dr. Pierre Berini. Pierre, whenever you're comfortable, go ahead and share your screen and get today's presentation started. Thank you again for joining us today.
Okay, thank you, Drew. I imagine you can hear me well.
Yes, I can hear you very well.
Here. Can you confirm that you're seeing my slide presentation?
Yeah, once you go to, I think hit display settings and change the, yep. Awesome, yep.
Good, excellent. Okay, very good. So let me just get this bar out of the way here. Whoops. Okay, we're still good, right, Drew?
Yes. Good to
okay. For the invitation to participate in this series. It's a great pleasure to be here to talk about my favorite topic, plasmonics and their applications in various fields. I have listed 4 things that I wanted to briefly touch upon today to introduce people to this very exciting area of nanophotonics and to exemplify the diversity of applications that stems from nanoplasmonic applications. So we're going to touch on a number of fairly disparate topics that all have as the underlying theme the use of nanoplasmonics. So I'll talk a bit about some optical antennas that are based on nanoplasmonics and how they can be used for several applications. I'll talk a bit about colors and how one can render colors using plasmonic nanostructuring. I'll talk about the use of plasmons for biosensing applications. And I'll talk a bit about the use of surface plasmons for catalysis applications in chemistry. So 4 sort of disparate areas. So if you find something boring, then hang on because we'll change topic fairly quickly and move on to the next one. I'll start with my last slide first because the last slide lists everyone that's been involved in these projects that I'll talk about, mostly graduate students that are carrying out their PhD or master's thesis work in my group on the work that I'll be discussing today. Students in the group come from different walks of life. In terms of backgrounds, we take students from physics and from chemistry and from a couple of engineering disciplines, electrical and mechanical, and they all come in and connect into plasmonics from various perspectives and carry out projects towards their thesis work in the group. So this is a fairly long list of the grad students that have worked or are still presently working on some of the projects that I'll discuss here. Projects have also been supported from various funding sources, including a couple of industrial sources. So the coloring work by the Royal Canadian Mint and some of our nano antenna work by Huawei Technologies Canada. So I just want to acknowledge that before I get started. And everything I'm showing here has been published or will soon be published. And these are the references from which I've drawn material to present to you today. So the first topic I'd like to talk about is antennas. So plasmonics is quite indeed heavily used to create resonant structures. And so a nanoresonator you could view as also being an antenna in that a nanoresonator can be made to couple with incident light. So you might illuminate a nanoresonator that is made out of metal with a plane wave and induce on that metallic structure a resonance. And we call these things either nanoresonators or nanoantennas, depending on the sort of geometry or the sort of structure. So the sketch that you see here is a sketch of a very typical nanoplasmonic structure. So we have 2 metallic rods shown in yellow. These are gold rods. So we like gold quite a lot in plasmonics because The material is unreactive. It's quite inert, and so one doesn't need to worry too much about chemical interactions with the environment of the nanoparticles. Forming nanostructures from gold is fairly easy. And gold is also a very good plasmonic metal. So what's a metal actually at optical frequencies? The sort of the zeroth order approximation to a metal would be, let's say, a perfect electric conductor, an electric wall, as we often say in electromagnetics. But that's not really a very good representation of metal. It might be the zeroth order approximation. When one looks a bit more carefully at the material properties of metals at optical frequencies, one finds that a cold plasma model, the Drude model, as we often call it, represents metals best, or represents metals very well, actually. And what that model says is that a metal is essentially comprised of a gas of free electrons that are able to move around and slosh around inside of that metallic structure. And so because it's a gas of free electrons, the relative permittivity of the material at optical frequencies ends up having a negative real sign, as opposed to normal dielectrics where the permittivity is positive. For example, 1 for air or vacuum, and 2-ish for glasses. And higher for semiconductors. Well, for metals, the relative permittivity is actually negative. And the consequence of that, from an electromagnetic standpoint, is that a surface wave can be supported on the metal when it's in contact with a normal dielectric like air. And so if surface waves can be supported, then you can create small resonators of the kind that are depicted here, where we have surface waves that are moving back and forth along the structure. And then the geometry starts to dictate where this thing will resonate in the spectrum. As you can imagine, this looks very much like a resonant structure where surface waves will reflect back and forth on the system. And so there are going to be some wavelengths where those surface waves will reflect and form constructive interference conditions, kind of like a Fabry-Perot cavity. And that will dictate where in the spectrum, in part, these nanostructures are going to resonate. So this is a very typical plasmonic nanostructure, as I was saying. It consists of a pair of nanorods that are coupled together with a very small gap, which is shown here as G. And if one then sends light perpendicularly incident on the structure and calculate what is reflected and then what is transmitted through the structure, one can obtain the transmittance, the reflectance, and the absorptance of this nano antenna structure. And here's a graph of what that looks like. So the blue curve is the transmittance. And so you can see that at a specific wavelength, which is in this case around 1300, the transmittance shows a minimum. And that is indicative of incident light coupling to the nanostructure. Specifically, it's exciting a resonant mode, the main one that is supported by this nano antenna. Because metals are also optically lossy, they're a cold plasma, but the electrons that are free to move in the metal are actually almost free. They're not quite free. They can scatter. They can scatter with lattice ions, and they can scatter with other electrons, and that causes energy losses. So a metal is, in fact, optically also lossy. And that loss has as a consequence that one would see a very strong absorption, as shown in this red curve here, when exciting in a plasmonic nanostructure on resonance. Okay, so two characteristics that are telltale signs that you have excited a resonant nanoparticle. A metallic nanoparticle is a very high absorptance at a specific wavelength, which is approximately coincident with a dip in transmission when measured on the other side. Okay, and this is indicative of having excited a plasmon resonance on the nanostructure. If one looks at the near fields on such a nano antenna, one finds that those near fields, in fact, can be significantly enhanced relative to the incident electric field. So if we are coming in, for example, with 1 volt per meter of incident electric field in a plane wave, you can see that the near fields will reach values that can be of 10 to 100 larger, depending on the geometry of the structure. So for example, for a very tightly spaced pair of nanorods where the gap is very small, in the gap, fields can reach extremely high values relative to the incident field. So if you're coming in with about 1 volt per meter, then the electric field inside of this gap can reach values that are 10, 20, 30 times higher, depending on the size of the gap. So this has implications for light matter interaction occurring, let's say, in the gap. So if you put a nonlinear material, for example, in the gap, then that nonlinear material is now seeing an electric field that is effectively many, many times larger than the incident field. And so one would expect enhanced nonlinearity to occur with these surface plasmons. And indeed, this is one of the main reasons why folks are interested in nanoplasmonics, is because of these enhanced fields that can be exploited in nonlinear processes and in other light matter interaction processes that I'll talk about briefly today. These fields that you see here are associated with the main resonance of the nano antenna. So the wavelength, for example, where we saw that big absorption peak on the previous slide. So almost all nanoplasmonic structures can be understood in this way. Here I've shown a pair of nanorods, which we call dipole antennas, because they look like microwave dipole antennas. But a single nanorod behaves very similarly. Nanoparticles, spherical nanoparticles, for example, will also behave similarly in the sense that they'll show resonances and enhanced fields. And so there's quite a lot of work being done at exploring the details of all these geometries and how things change with geometry. But fundamentally, there's always the main resonant mode that's there, the main dipolar resonance, as we call it, that couples with incident light, and around which you'll have strong enhanced fields. Here is one device application where we make use of these resonant nano antenna properties. This here shows a photodetector where the metal contact that's used to bias the photodetector is also structured as an array of nano antennas. And so this photodetector is expected to show spectral selectivity properties, so enhanced detection at specific wavelengths, in other words. And because it's created as a Schottky contact detector, one expects that it's going to work below the band gap of silicon, which is what was used in this case, extending the photodetection range, deeper into the infrared. Here in this concept, we're exploiting the absorption peak of the nano antenna as the main feature. So the nano antenna on resonance is going to absorb a lot of that incident light. That's why we see this absorption peak. So where's that power and energy going if it's being absorbed by the nano antennas? Well, where it's going is in exciting carriers inside the metal of the nano antennas. So the electrons, for example, in the nano antenna metal gain energy, holes gain energy. And so you have a population of hot carriers or hot energy or energetic carriers inside of the metal due to this optical illumination. And those energetic carriers can be emitted outside of the metal and collected in the semiconductor as the photocurrent. And that's what this sketch on the right here shows. This is an energy band diagram of a gold silicon p-type structure where we've created energetic carriers in the metal through this absorption. And then these energetic carriers, if they're heading towards the semiconductor, can be emitted over the Schottky barrier and collected as photocurrent. So this is a photodetection mechanism that extends detection into the infrared. So that's why it's interesting. It exploits the absorption of plasmonics through the absorption of light by the metal. And it adds wavelength and polarization sensitivity or selectivity to the detector, which is of interest in some applications. So here's an image that shows the fabrication of such a detector. Here are the nano antenna arrays that go to a contact metal here that we can probe. And then you have higher magnification images of these electrically contacted nano antennas. and some measurements where we see here the photocurrent that is measured as a function of optical wavelength. And so the absorption peak that I'm highlighting down at the bottom here, associated with the nano antennas, is well replicated by the envelope of these responses. Okay, so we can quite clearly see from these responses the nano antenna wavelength response convolved with the detection response. And then these fast variations that we see in the response here are simply due to Fabry-Payot reflections in the substrate, because the substrate is reasonably transparent. This other experiment that I'm showing here now pulls out the other feature of interest in using plasmonic nanoparticles, namely the enhancement of electric fields in the near field. As I was showing earlier in that second slide, fields are very strongly enhanced around metallic nanoparticles on resonance, and that strong field enhancement can be used to drive and improve a nonlinear optical process. So in this experiment, which was carried out in collaboration with the group of Paul Corkum and Giulio Vampa at the University of Ottawa, in this experiment, we created these gold nano antennas. They're simple nanorods that resonate similarly to what I was showing earlier with surface waves that resonate back and forth, with very strong fields near the tips and around the outside periphery of the metallic structure. So these were designed to resonate at the fundamental wavelength of this experiment, the driving wavelength, which was about 2 microns. So these nano antennas resonate at 2 microns. They're illuminated in a fairly simple setup, and then we grab the emission on the other side using a UV vis spectrometer and look at the harmonics that are generated. And we see quite a large number of odd harmonics, all the way up to the 9th harmonic, which is this little red bump that you see here. So these are the measurements, spectral measurements. This is the 5th harmonic, the 7th harmonic, and this is the 9th harmonic. And these are all generated in silicon. And the difference between the red curve and, let's say, the black curve is that on the red curve, we are using the nano antennas. And for the black curve, we're away from the nano antennas in a bare substrate area. So one can immediately observe that by making use of this plasmonic field enhancement effect, we can achieve an order of magnitude higher emission of these high harmonic signals relative to the bare substrate. So this is the electric field enhancement process that I was talking about a bit earlier. The nonlinear mechanism here is a non-perturbative recollision radiation mechanism that was evolved in the group of Paul Corkum and several others throughout the world, where electron hole pairs are forced apart in the semiconductor by the strong electric field, and then redriven to recollide. And in that process, they give off harmonics. Here's a third application of nano antennas, where again, we make use of the strong field enhancement of the nano antennas, but not for a nonlinear process, rather to enhance an electro-optic process. In particular, an electro-optic process that will modify the phase of the nano antennas, aiming to achieve an optical beam steering device that is similar to what you would see at microwave frequencies. So if you think of a microwave beam steering device, you'll have a source that then is split into several channels, each phase shifted separately, that go off to antennas that radiate. And depending on the phase shift profile that is applied, the beam will, in the far field, form a preferred direction. Okay, so that's how one can achieve beam steering at microwaves using a single source. If we apply the same model using nanoplasmonics and light, then what we need to use, of course, is a laser. And then we need to have different channels where we can modify the phase and then radiate that light from those channels to create in the far field beam steering. And so this is a job that can be done using plasmonic nano antennas. This blue matrix here shows at a high level what is the job that needs to be done. This would be a pixelated mirror, if you would like. And each pixel, as highlighted here, has a variable phase. the magnitude of reflection coefficient should be approximately 1, should be unity, so all the light that hits it should come off. But the phase of that light that hits a pixel should be variable between 0 and 2 pi. And if you can achieve this in a 2D pixel format, then you can steer the beam just by varying the phase of these pixels to any desired reflection angle within, a certain range. So if one imagines that these pixels here can be formed of plasmonic nanoantennas, as sketched here, that are electrically connected, and if one then can design these plasmonic nanoantennas so that they produce a phase shift, so here's a calculation that shows the phase shift from an optical nanoantenna as a function of drive voltage. This is a MOS capacitor structure, by the way, where we have the gold nanoantennas that form the metal contact. This deep blue oxide is the oxide of the MOS capacitor, and an ITO is used as a semiconductor, which also has a so-called epsilon near zero regime in the wavelength range. So if we drive electrically this MOS capacitor while exciting the nanoantennas on resonance, then during a carrier accumulation in the MOS capacitor, we're able to shift the phase over quite a large range with a reasonably constant magnitude of reflection. So this is what's desirable, of course, to create a beam steering phase shifting array. And so after a fair bit of design, we built some. This is a SEM image, a microscope, helium ion microscope image of nano antenna array connected to fan out fingers that can then drive this nano antenna array in the same sort of way. And the purpose of this array is to indeed implement, as I was showing on the slide earlier, phase shifting pixels that allow beams to be steered in different directions. So there's a very strong interest in this sort of a beam steering device for applications such as LiDAR, for example, okay, on cars where you might not want to have mechanical moving parts or liquid crystals, which could be problematic. Having a pure solid state, semiconductor-based optical beam steering device is something of quite strong interest in industry. So that's on the nano antennas, and gives you an idea of what one can do in nanoplasmonics with nano antennas. Okay, so enhancing nonlinear effects, beam steering devices, optoelectronic applications like photodetectors, modulators, and lasers as well. And there, what one exploits is the enhanced absorption or the enhanced fields of a plasmonic nanostructure. That's the key. Those are the key reasons for using those in those applications. It turns out that the enhanced absorption of plasmonic nanostructures can also create colors when one looks at nanoplasmonics with in the visible range, of course, with white light. And so I'd like to talk briefly about the generation of colors using nanoplasmonics, because that's quite an interesting and visually appealing topic, actually. So the oldest known plasmonic coloring or colored device is, to my knowledge anyways, the Lycurgus cup, which is on display in the British Museum. This is a cup that dates back to the 4th century after Christ. And it's made of a dichroic glass. So what this means is that it produces a different color depending on how you're illuminating the device. So for example, the cup appears red when you place the light source behind the device. The cup appears green when you place the light source in front of the device. So in transmission, the cup is red. In reflection, the very same cup looks green. So that's what's meant by a dichroic glass. It shows two different colors depending on how you illuminate it. Where does the dichroism come from? Well, actually, it comes from colors that are generated by scattering from metallic nanoparticles that are dispersed in the glass. So if one looks very carefully at what's inside this glass, one finds metallic nanoparticles, and it's those nanoparticles that are responsible for the color that's rendered. Here's a nice summary of how that might happen. So small nanoparticles vary in shapes and size. And as they vary in shapes and size, their resonant wavelengths will vary to different locations in the spectrum. And as we saw earlier at the very first slide, a plasmonic nanostructure can exhibit a resonance, and on that resonance, a very high absorption. So if you have a spectrally localized high absorption, that means upon illumination with white light, that a certain part of that white light spectrum gets absorbed and the rest of it gets reflected. And that fundamentally is where the color comes from in these nanoparticles. So for example, here you see vials of mostly aqueous solution that contains in there a suspension of metallic nanoparticles of different shapes and sizes. And if one then measures the absorption using a spectrophotometer, for example, of these solutions, one obtains the following set of curves. So this is absorption versus wavelength. So for example, here's an interesting case number L. Case number L shows a large absorption at longish wavelengths, a lower absorption right around 500 nanometers, and then a bit of a peak here at even shorter wavelengths. So this is how case L absorbs incident light. So you're in the visual part of the spectrum here. So what this means is that the reds, which are over here, are being strongly absorbed. The blues, which are there, are being strongly absorbed. And then right in the middle where green lives, you have minimum absorption. So you get a strong reflection of green light effectively from the structure. And that's why the vial looks green. Okay, so the absorption, the color is generated by spectral subtraction, if you wish, due to absorption of these metallic nanoparticles. So that's a very useful feature that can be used to create things like biosensors or even decorative applications, of which I'll talk about briefly now. So we were approached several years ago by the Royal Canadian Mint, who is responsible for minting coins for not only Canadian consumption, but for about 150 countries around the world. It's a big minting operation, and they have a collectibles business. Not only do they mint circulation coins, but they also mint collectible coins. And for their collectible business, they were interested in a direct laser write process to color on silver. So we developed then, in collaboration with the Mint, this laser direct write process to induce color. You can see here one of the palettes that was generated on one of the color palettes that was generated on a silver coin. These are not painted or dyed or anything. It's only illuminated by laser. And so what we do is effectively we raster scan with a burst laser system and control all the parameters of the writing process, which we develop, an understanding of empirically to come up with these color palettes you see here. So color palettes can be quite broad, and colors can be indeed quite vivid, depending on how one shapes the pulse streams, as shown in this various diagram here. And the colors can cover quite a large part, actually, of the color space. Not complete coverage of the color space, but reasonably good coverage of the color space. I think we have still a bit of trouble with the greens, but because you need to sort of absorb two parts of the spectrum, as I was showing a bit earlier with green, but the other colors are somewhat easier to generate for that reason. So this plots chroma versus hue, and the more you can fill in this graph, and the more color, the more of the color space you can actually fill in. This is also another way of rendering the size of your color space, with displays sort of being limited to a triangle that's somewhat larger than the region that we can cover, but we cover still nonetheless a pretty good region. And the reason why this works is because upon application of laser to the surface, we ablate material, which then condenses in air in the form of droplets that then redeposit on the surface of the structure. So we end up with these tiny nanoparticles that you see here all over the surface. And as we saw a couple of slides ago, nanoparticles can give off color depending on shape, size, density, that kind of stuff. So that's where fundamentally the colors come from. So this generates a nice deep blue, as you can see here, from this visual camera representation. Sometimes we see ridges as well that form, so lips, which are known to be created when one illuminates with a laser. And then we applied this process to coins of various kinds to sort of enhance their visual appeal for the benefit of the mint. They're all laser colors that you can see here applied to different coins. Here's sort of the main piece that drove this. This is a large collectible silver coin. It's 20 centimeters in diameter, and it weighs 5 kilograms. So of course you won't drag this around in your back pocket. It's meant to be displayed, on in a cabinet somewhere, rather than to be circulated. But they can't color this, other than by hiring a painter to come in with paints and stuff to individually color them. They have no process for coloring these very large collectible coins, and it's for these coins that the laser writing process was developed. Here, there's a lot of topography here on this surface as well. So the nose of the bear that you can see here, this is a Haida art representation that was created by the Haida in the west coast of Canada. So they also have totems, for example, that are very beautiful. So they created this image that was then rendered on coin with topography. So the nose of the bear sticks out from the surface of the coin by maybe 2 or 3 centimeters. And then there's trenches around the eyes here that go down about 0.5 centimeter or so. So there's quite a lot of topography on this surface. But nonetheless, with a laser writing process, you can color various aspects and various features, as we show on these collections of images here. So purely a decorative application, but nonetheless a very valid one, because everyone, I hope, appreciates the beauty of colors and the beauty of art. Changing gears, the use of nanoplasmonics in the world of biosensing is indeed quite prevalent. And I have no opportunity here to give you an appreciation of just how broad and how wide this field is. But in fact, this is one of the areas where plasmonics has had the greatest impact in terms of applications, but also in terms of commercialization. So there are companies out there that are manufacturing and selling optical biosensors that are based on plasmons. So it's quite a large business. And so that, of course, comprises part of our activities as well. So I'd like to briefly talk about that too. So for the biosensors that I'll be discussing, we make use of plasmonic waveguides. So this is a bit different now from the nanoparticles and the nano antennas that I was talking about earlier. These are now waveguides. If you were to think of these structures as being sort of integrated optical structures, but using metallic stripes, which is what these yellow stripes here represent. These are all gold stripes that are shaped in various ways. Then you would be thinking about this in a reasonably accurate way. These are indeed integrated optical circuits where the waveguides are metal stripes and the surrounding environment is dielectric and or fluidic. So we were saying a bit earlier that plasmons have very strong enhanced fields, which is true. They are also localized to the surface of the metal. So they're also highly surface sensitive. So if anything happens along the surface of the metal, while you've got a plasmon propagating there, then you will be affecting the propagation properties of the plasmon. And it's that characteristic that is exploited in all plasmonic biosensors, be they waveguide or nanoparticle based biosensors. And so how one exploits this is then sketched here. So here's the top surface of your gold sensing surface, your waveguide. Here's the plasmon with its enhanced and strong fields localized to the surface. That plasmon propagates along the metal. And so if there's a biomolecule that is attached there, then that will disrupt the propagation of the plasmon. So its attenuation will change, for example, and its phase constant will also change due to the presence of biomaterial, okay, which has an optical refractive index. So a biomatter has an index of around 1.4, 1.5, depending on where you are in the spectrum. And usually the biomaterial is surrounded by water, which has an index of 1.3 or so. So there's an index contrast between biomaterial and water. So if biomaterial replaces water, then locally you've raised the refractive index of the environment. And that change in refractive index is what is sensed by the surface plasmon waveguide. So to make a biosensor then that is specific, one would attach receptor molecules shown here as these Ys. You could think of these as an antibody, for example, that is specific to the bio partner of interest to be captured, which is shown by these orange spheres that you see here. So this could be, for example, antibodies against a soluble marker that indicates a disease state in a patient, and then that soluble marker binds to the surface. So when the soluble marker binds to the surface, then the surface wave is altered, and you can detect this as a change in signal and then monitor these events in real time. So we've been using these waveguide structures here as biosensors because of this property that they're very surface sensitive. In order to have a biosensor, you need several components. You need the sensing waveguide, as shown here, with the ancillary optoelectronics, so the lasers and detectors on the outside to interrogate the waveguides. You also need to be able to manage fluids. So you need to integrate microfluidics in some way. And then you require surface chemistries, as shown here, for rendering the biosensor specific. So you typically need to address four things: surface chemistry, microfluidics, the transducer itself, which is, let's say, the waveguide, and then the ancillary interrogation optoelectronics. And until all those four things come together, you don't have a biosensor. So, okay, this is a fabrication slide that shows how we fabricate these things to create the sensing waveguides on one side, and then the microfluidics on the other side. And then we have one wafer with microfluidics, the other wafer with the sensing waveguides. And then we bond these things together using a wafer bonder to have a fully integrated structure with sensing waveguides and fluids. And then we place this in an interrogation setup where we send light into the input, collect light from the output, with fluids being pumped in and out of these channels. So here's a result, for example, where all we do now using a straight waveguide biosensor is change the sensing fluid and its refractive index for different values. So then you see some very clear steps in the output power versus time as we switch in different solutions with different refractive indices. This here requires, of course, that you be able to do the fluidics, the optics, the ancillary interrogation system, but doesn't require any surface chemistry because it's non-selective at this stage. It's just bulk fluids that we're sending in. But it's a great way of testing the underlying technology. So the sensors, the fluidics, as well as the ancillary optoelectronics, which you need to debug for stability and high quality signal acquisition. One can get a little fancier. This is a multi-output Young's interferometer. So we send light into the input here and then split it into two ways and then two ways again with microfluidics and center channels that provide references. That provides 6 outputs, which you can see here as these 6 spots. We can then merge those 6 spots together using optics to create one large and messy interference diagram that you see here. And then if you look at this in the spectral domain through Fourier analysis, you can identify peaks that are associated with a specific waveguide output interfering with a reference. And that's how one can do multi-channel phase-based interrogation as opposed to attenuation-based interrogation. And it makes use of the integrated capability of being able to put lots of waveguides in a complex design on a chip. So here's a slide that shows all of these channels being monitored simultaneously as we switch in solutions of different refractive indices into the system. So that gives you sort of 2 ideas of how, from a technological standpoint, you might implement a biosensor. But bulk sensing is not all that interesting. What's most interesting is if you're able then to translate this into disease detection problems, which we've done. So this slide introduces the idea of doing leukemia detection based on the detection of soluble markers, so markers that are in patient samples, in patient blood, for folks that have leukemia. And in working with an oncologist around the definition of this problem, we determined how to discern leukemic blood from normal blood, what to look for in leukemic blood versus normal blood. And then we functionalized our waveguides to be able to do this. So this slide here kind of shows the functionalization approach, where we apply proteins to our waveguides and then antibodies. And then we select antibodies, 2 different types of antibodies, and look for 2 different concentrations. And from that, we can determine whether a patient sample is leukemic. So this brings in that 4th element that I was talking about earlier, namely the need to chemically functionalize your biosensor to render it specific, right? In addition to the fluidics, the optical transducer, and the ancillary optoelectronics, you need to chemically functionalize. So this is how it was done here, using antibodies targeting the detection of leukemia specifically. Here's a sensorgram, which is the output power versus time, as we injected a leukemic patient sample in the device, and then show the various chemical interactions that are occurring on the surface. And then by analyzing the signals, we're able to say, yep, this is a normal patient, or unfortunately, it's a leukemic patient. Yeah, we compared this against lab results with excellent agreement with conventional chemical techniques for identifying leukemic patients. One more slide I'd like to show is on catalysis, which is yet a 4th topic that's somewhat distinct, but connected to the properties of surface plasmons. The very first slide that I was showing on the nanoantennas, you'll recall, showed a very large absorption peak in the spectrum. And we said that absorption peak is because the metal is absorbing incident light and it's going into hot carriers, which we then used for photodetection. Well, another place where you can use hot carriers on a metal surface excited by plasmons is to catalyze chemical reactions. So this one slide captures some work that was very recently published by our group, where we have been experimenting with the decomposition of CO2 gas. So the connection here, of course, is global warming, and the fact that we have lots of CO2 that's being produced from various sources. And what do we do with it? We're in Canada, we're basically pumping it underground to fill in old oil wells or old mine shafts, and expecting geology to take care of CO2 over time to turn it into carbonates and different rocks. We are also putting it into cement. That's another good way of getting rid of excess CO2 to again form a carbonate, but that's now part of cement. So we got interested in seeing whether we can actually decompose CO2 into its atomic constituents, namely oxygen and solid carbon. And we approach this with a view towards exploiting hot carriers on plasmons. So here's the plasmonic structure. It's nothing more than a simple grating structure, which we illuminate with incident light that causes a resonance to occur. Here's a SEM image of the grating structure. And then that resonance has an absorption peak, like the antenna resonance I was showing earlier. And with that resonance are accompanied absorption of, we're creating hot carriers due to the absorption of light on resonance. And these hot carriers are all on the surface and available to react with, an environment. So in our case, the environment was CO2 gas, which we pumped into a windowed gas cell while illuminating these plasmons. And then we monitored what was coming out optically from this system using a Raman microscope, driving this at 532 with green light, essentially a green laser. We're seeing very large changes in the Raman microscopy signals. And in particular, a couple of peaks here that show the formation of solid carbon that are indicative of graphene-like materials on the surface. And when we then carry out a very careful inspection of that surface, we can see these carbon deposits, solid carbon that's forming directly on the grating as very clear hemispherical deposits. So using this process, we're able to decompose CO2 gas directly into its constituent elements, namely oxygen that blows off in the chamber and solid carbon that forms and deposits on the gratings. And that's an example of what folks call hot carrier catalysis or hot carrier chemistry. Namely, we create hot electrons, hot holes, and then make sure they're available to react with a molecular environment, and then see if new decomposition channels open up or if new reaction channels open up, because you have a population of energetic electrons now that can participate in chemical reactions. And here is one example that you can find in the literature, which was published by us on the decomposition of CO2. So this is quite an interesting and exciting project, because getting rid of CO2 is a problem, as I was saying earlier. So this brings me back to my second slide, which is highlighting the fact that this is all work that's done by students in the group as part of their PhD or master's theses or their postdocs, or sometimes technologists that work in the group. And there's literature here that you can read up on some of these topics if you have an interest. And this brings us to the end. I have no more time left, so I think I'll stop at this point.
Awesome. Thank you very, very much for presenting today. Looks like we do have a couple questions in the chat that you won't be respectful of your time. So if you would not mind, I would like to get into those real quick.
Yes, please.
The first question says, I guess the first question will actually be from OPCA membership. And it says, can your biosensors be applied to the detection of other diseases?
Yeah, so I talked about leukemia here. Mm-hmm. But as I was mentioning during the presentation, the selectivity of the biosensor is in the chemistry that one applies on the surface for the target analyte. So if you want to change disease, you change the surface chemistry. The underlying technology remains the same. The waveguides, the fluidics, the ancillary optoelectronics remain the same. So if you're interested in, for example, COVID detection, as many people might be, then we need to apply surface chemistries that are going to be selective to virus fragments of COVID or antibodies that were generated by patients in response to COVID as a means of detecting that particular disease using these waveguides. So they're absolutely applicable to other disease detection problems. Mm-hmm. It boils down to changing the surface functionalization on the device.
Okay. Looks like I'm going in order, and I apologize, everyone online, if I butcher any names. It's a disclaimer, it's not my intention. But a question from Srinivasu says, could you briefly explain how does the tunability works in the optical phase array?
Yeah, so I went through this extremely quickly, but one thing I mentioned was that the optical nanoantenna structure is actually a MOS capacitor, a metal oxide semiconductor capacitor, where the nanoantenna is the metal. We have hafnia as the oxide and ITO as the semiconductor. And when you bias that structure into accumulation, you get carrier accumulation along the oxide close to the metallic region. And through the carrier refraction effect, a high carrier density changes locally the material properties. And in fact, in ITO, a high carrier density changes the refractive index so much that it goes through zero. The real part of the permittivity goes through zero due to the accumulation level that's achievable in ITO. And then by changing that refractive index locally close to the nanoantennas, the optical properties of the nanoantenna changes, namely its phase upon reflection. And that's what we're exploiting to do this electrically tunable phased array. So you'll find details of that in this paper here that was published recently in JSTQE.
Awesome. The next question I see, so it looks like we had two questions from Srinivasu. The second question is, how does the solid state optical array have advantage compared with liquid crystals arrays?
Yeah, so there are many. There's also disadvantages, which we, as engineers, we always have to highlight, even though we often fail to do so. So first, the advantages, solid versus liquid. There's already like a major distinction there between the material types that you're using. So if you have a liquid crystal, you need to manage a fluid. So you have to figure out how you're going to do that in the fabrication of your device. Whereas if it's all solid, well, then it comes down using semiconductor manufacturing processes as usual, without having to worry about encapsulating a fluid. Other thing, if you have a fluid, then the temperature affects its properties quite significantly. So for an automotive LiDAR, this is a big issue because just in Canada, Canada actually has one of the largest temperature excursion ranges that you could think of on Earth for automotive applications. Winter is -40, and in the summer, these days we're getting into the +35s or so. So you've got almost an 80-degree C range there that you need to cover for automotive applications. And liquid crystals are problematic at -40, and at +40, they have very different optical properties. They're also very slow upon actuation, so it's not easy to scan quickly. The solid state approaches don't have those disadvantages, but they have the major disadvantage that none of them have yet been demonstrated to actually work very well. What I've shown here is concepts and approaches to carrying this out, but there's a review paper that's going to come out in a couple of weeks in ACS Photonics, where I look at the entire state of the field, and really there's not much out there yet that from a quality standpoint can actually do decent beam steering, but the opportunities abound. And that's only because the field is in its early days, and we're still working towards improving device ideas and improving fabrication. Ultimately, we can get closer to good performance.
Awesome. Looks like the next question we have in the chat is from Reinhard Paul. It says, what are the advantages of plasmonic waveguides against photonic waveguides and vice versa?
Yeah, so this is with regards to the biosensors, right? So from the optical standpoint, the plasmonic waveguides have a higher surface sensitivity because the fields are enhanced and large on a plasmonic surface compared to the dielectric waveguide. So you have a higher surface sensitivity, but you have attenuation that you have to manage. So it doesn't mean that you always win necessarily on that spec, because even though a dielectric waveguide might have a lower surface sensitivity, they can sometimes be longer and have higher overall sensitivity because they're longer. But that's kind of a disadvantage because you need more length now to be able to achieve sensitivity. But the real difference comes into the chemical functionalization. So gold actually, as it turns out, is very easy to functionalize chemically, especially if one is using thiolated self-assembled monolayers, which form spontaneously and in very high quality on gold. Functionalizing a glass surface can be done, and of course it's done in various schemes, but it's more difficult and it requires a bit of thermal processing. So there's an advantage on the functionalization side for gold surfaces.
Awesome. Question from Morteza Malachi about the CO2 decomposition. How about the effects of the deposited carbon after decomposition? In other words, how about the lifetime stability about the grading?
So once the carbon deposits form on the surface, as we can sort of see it here, it's permanent. We can reverse the reaction, which I didn't talk about, but if you turn the gas off and go back to air, you can get the carbon off by having it react with oxygen again and be released as CO2. So that's kind of counterintuitive to what we would like to achieve. The other thing I failed to mention is that these carbon deposits actually emit light. There's carbon quantum dots that are being formed in addition to these larger deposits. This is a camera image, so you get yellow light coming off of these things. that's quite visible using your cell phone camera. So they're light emitting carbon deposits, actually. I think if we passivate the surface, this becomes sort of a permanent optoelectronic device. So it has applications, let's say, in displays or light emitting metasurfaces. But then the environmental question has to do with the carbon deposits themselves and how one can use them, let's say, in a carbon sequestration application.
Awesome. Looks like we have another question in the Q&A for Christine Steenkamp. In the high harmonic generation in silicon, how does the intensity of a specific harmonic change with the intensity of the fundamental laser? Is the fifth harmonic intensity still proportional to the fifth power of the fundamental intensity?
Nope. Excellent question. Nope. In fact, I don't know if I have time to scroll back here. Just to the main result, which was the spectral plots. Yeah. So here's the fifth harmonic. There's the seventh. There's the ninth. They don't scale with the power laws that you would expect from perturbative nonlinear optics. And the key word is perturbative, right? So when you read Bob Boyd's book, who's a colleague here at the university, his book is based on perturbation theory. This is a non-perturbative process. The nonlinearity is non-perturbative. So it's due to recollision radiation, as I was kind of alluding to a bit earlier, which is something that Paul Corcom's group's been working on quite intensively. And so that doesn't scale with the power law that, Bob Boyd tells you that it should scale with. Because it's non-perturbative.
Mm-hmm. Looks like, okay, we have one more question in the Q&A.
Okay.
Question is from Morteza Malachi. Question is, plasmonic sensors have a wider, and you might have to help me with the acronym, FWHM. Despite the functionalizing, are they better than dielectric sensors?
So this is the resonant behavior. So the acronym mentioned is the full width at half max, which is the width of that resonance. So plasmonic resonances tend to be rather large. Spectrally, dielectric resonances can be much, much sharper. That has implications on how easy it is to track it, changes in the spectral domain when you're doing a measurement. So a sharp peak is easier to follow than a sort of a fat peak that's moving around. But it doesn't speak to the sensitivity of the detector. It speaks to the detection limit, for example, which depends on how easy it is to track, but not so much the sensitivity. The sensitivity of plasmonic resonance systems remains higher than, in general, dielectric resonance systems. I think this is something we keep seeing again and again in the literature. But because it's fatter, it's a bit harder to track. So you might lose out there because it introduces an uncertainty in motion of a spectrum or changes in the spectrum when the spectrum is large. And that has implications on how small of a change you can detect. So it does play in ultimately on the detection limit of the sensor. But it's an important consideration along with the sensitivity to think about how you're going to monitor a fat resonance over time.
Awesome. It looks like that we can wrap up the Q&A right there. Definitely want to be respectful of Dr. Pierre's time. Everyone online, thank you for joining us today. I will go ahead actually share my screen now. Just read a quick little outro from my Optical Membership Programming and Science Software today. Just be reminded, we do have one more engineer program going on today, starting off in about an hour with Veronica Hernandez. Dr. Pierre, I will go ahead and share my screen now. So once again, thank you everyone online for joining us today. Thank you, Dr. Pierre, for the presenting. I know I talked a little bit before we hop on the webinar, but I think